interesting. All right, hi everyone. Thank you for attending. Thank you for being here. You sticking around. My name is Vokshi, as I was mentioned. What I do at Sika is what I tell my 6-year-old daughter is I make buildings stronger. In that capacity, I support engineers and contractors from the design and specification phase all the way to installation phase with various technical questions. I also cover some of the corrosion products as well, but really my passion is in carbon fiber systems, and I've been doing it for, I would say, you start losing track of time, but I would say good 12 years now in different capacities. My background is in structural engineering. I have a master's degree from Arizona State University, where actually my master's focus was in body armor. A little bit different, but still composites. All right, so today, my presentation today is not so much research-driven. It's more on application side of what we're doing with these different systems in the industry. It ties in, though, with the discussion of extreme events, as a lot of these applications have to do with those. So what I'll talk about is, build my story on why we strengthen structure, and then I'll talk about, how this active post-tensioning system works, and then I'll show some good case studies with the product. So why we strengthen structures? Obviously, I think we can all agree that structures are strengthened because there's some sort of a structural deficiency that somebody has determined, an engineer. This can come due to corrosion damage. It could be because of a change in use. It could be due to a structural damage, like an impact on a bridge, for example, or even, of course, seismic deficiency and the requirement for seismic upgrades. So when an engineer is considering structural or strengthening in general, they have a couple of options. Externally bonded FRP or steel is one of the options that, obviously, we all participate in this market and love it. I would say what used to be done with steel, more than 70 to 80% of it can be done with just externally bonded FRP, though obviously there's a lot of limitations that many of us are aware. Of course, if that doesn't work, there's always section enlargement, adding additional weight and rebar to the structure, but one that's still a well-used method. External post-tensioning, this is what I'm focusing on today. This is another method for strengthening. Most of it traditionally is done with steel, I would say even today. I'm going to talk about this new solution, how we can implement it with FRP. And then, of course, if none of these work, there's always addition of supplemental supports like adding bead or columns. Again, to build my story, there's various types of solutions that we have in the market, right? Wet layup systems, or as we call them, externally bonded systems. Protruded carbon fiber, which are still considered, externally bonded FRP systems. These are pre-cured laminates, right, that come in various widths and thicknesses. Other systems include the near-surface mounted rods. These are the carbon fiber rods. So usually we're installing on top slab applications. And then post-tensioned FRP plates, which is my focus of the discussion is today. And then I think we've seen a couple of presentations here on the FRCM system, which is that carbon fiber that's embedded in cementitious material. So why post-tensioning with carbon fiber? So I think the best way to summarize, and that I like to tell the story if I were to describe it to somebody in basic terms. When we're installing externally bonded FRP, that's a passive system, right? That sits in the structure until an additional load is installed, at which case, the carbon fiber is engaged. Whereas when we're dealing with a post-tensioning with carbon fiber system, this is now an active strengthening system, meaning the moment you install that structure, you're alleviating some of the stresses in the structure, but more importantly, you're addressing deflection or serviceability cases. In addition, and I think my next slide covers it, one of the limitations that we know with externally bonded FRP is that they're all bond dependent, right? You can utilize their strength as much as that bond allows you to. Beyond that, you can't really, you cannot utilize the ultimate strength of that carbon fiber. Because these systems don't have to be bonded, and right, you're relying on introducing the bond through these anchors that I'll talk about, we can utilize much more of the strength of the carbon fiber. This is a very basic, not that we would ever design something like this, but to give you a picture on what the advantage of this product is. If we were to look at those pre-cured laminates on a beam section, I believe this is a DOT type of beam, and if we were to increase the capacity for about 8%, you would need about 15 CFRP plates going in the bottom. Those are like 3 inches wide, so that's 15 divided by 3 is 5, so about 5 layers of it. Again, we would never do that in real life, but this is just to build my story. Whereas if we're utilizing this post-tensioning system, you can get about 26% capacity with 3 of these post-tensioned carbon fiber plates. So let's look at now how this product or how these systems work. So the post-tensioning can be, what we're utilizing them is for bridge strengthening. We're doing industrial high-rise or high-rise buildings, a lot of seismic retrofit, as I mentioned, and we even have some applications in water tanks or silos, which is really big diameter members where you can actually curve the carbon fiber. So the way the system works is very similar to your traditional steel externally bonded PT systems. You have a fixed anchored end and a movable end. What I'm showing here is one of the anchoring methods. We call this the shear pin method of anchoring, where we're drilling into the existing concrete about 8 inches or so, depending on the FC prime of the concrete, and on both sides. And then on one side, we have the movable end. The way the product works is you have the carbon fiber plate that's actually held together via this stress head that we call it, which is, it's actually a mechanically engaged system where the plate is pinched into that head that's circular. And then these steel plates, or on both sides here, hold the plate against the head. And then for the post-tensioning, I think this shows it here, we're introducing a hydraulic jack in the back there, having these 2 threaded rods in the end. And then by pulling it, you're post-tensioning the structure. And then once done, you simply tighten those bolts, and you can cut them if necessary or whatever. There's different methods to finish it off. But that's how the post-tensioning works. We're introducing about 50 kips maximum of post-tensioning load to these plates. I will mention that this is about 50% of the ultimate capacity, about 50%. But a lot of times, though, depending on the geometry and what the application is, we're looking anywhere between 30 kips to 50 kips of post-tensioning load per plate. Now, these plates can be placed next to each other, or in some cases, we've even done a case where you can actually place them on top of each other. So there's different ways to, where you can get more than 50 kips capacity. I talked about this shear pin. I think this is a bit more detail of how that's applied. Again, I mentioned it's about 8-inch depth or drilling into the concrete that you'd have to do for a 3,000 PSI concrete. This is one of the standard anchors that we have, testing for, and readily available, drawings and all that for users. Whereas as you'll see, you can get pretty creative on how you introduce the PT load, because obviously, as you can see, one of the limitations of this particular anchors that I'm showing here, not always do you have 8 inches. Actually, in most cases, you never have 8 inches that you can drill through to introduce this load. Another anchoring method is that's again standard, is the one where we do it for masonry walls, where we're sitting the anchor at the top of a slab, let's say on a high-rise building, and as well as here on the bottom of the slab to anchor that system, mainly again for seismic retrofit. This product can be installed in up to 800 feet long if necessary, but it's been applied for 10-foot floor building. Now, really, you can, the product, when it comes to the design itself, the majority of the intricacy of it becomes this: how do you introduce the load into your structure? As I mentioned, there are those 2 systems that are standard, but then you can get creative in terms of the engineering size on how we do that to make sure that obviously you're not cracking the concrete and you're not causing any damage around the area where the PT load is being introduced. These are different examples of anchors that we have been modified from the standard to kind of make sure that the PT load introduced is okay for the structure itself. I like this one. There's a lot of, because this product, by the way, is originated in Switzerland. They have a lot of application in Switzerland. It's been around for over 20 years now. And I like how they call it the Swiss lock on this one. Yeah. On the installation side, really, this is one of the big advantages, similar to the FRP systems, that it is very quick to install, it's very lightweight, and I'll show some case studies where you're installing in active conditions without having too much mobilization required to install it. So in general, obviously you're going to define the area and drill through in the area where you're installing those anchors, both the fixed end and the movable end, chipping if required, installing the anchor itself, injecting injecting or installing the anchor bolts and all that prior to the FRP installation. Now, I mentioned before, the product can be installed unbonded. We do recommend that it is, when installed, that you bond it just for protection more so than anything. If you wanted to utilize, the additional stiffness that you get from bonding it, you can. But really, this is completely optional. Another reason why we like doing the epoxy itself is because it acts as a lubricant when you're post-tensioning it, especially if you're installing it flush to the surface. If you don't have something in between to kind of, as you're post-tensioning to lubricate it, you may tend to damage a little bit of the carbon fiber strands at the very surface there. Now, obviously then that means, because we get this question a lot, can you let this epoxy set and then post-tension it? No, you can't, because you'd introduce ridiculous amount of strain on that bond line. So if you do decide, if an owner decides to install this as a bonded system, you have to install it while that epoxy is still wet. This is just showing a video of the installation. Now and I'll talk about this case study. This is in Slovakia, actually, on a bridge. And you can see in here, you can see how we utilize actually a lot of anchor bolts because we didn't have much cover to install to install that shear pin that I was talking about earlier. So on this job, like, they had to be in and out very quickly because it was a major artery to a scenic view. There's a video. So this is how they're installing the fixed end on this side, making sure all the anchor bolts are correctly drilled in. They're taking measurements to make sure everything is per the drawings. And then on that side, as you can see, they pulled it on the other side, and now they're post-tensioning it. Obviously, at this point now, the traffic is not allowed to move just in case, but as soon as that's done and they bolted, the traffic is back to moving. And this took about just the plate installation side about 20 minutes, just making sure everything is going smooth. And then the other end of the anchor, so this is the same job with the hydraulic jack. You can see in here how they're pulling the plate and how the deflection is happening. So I guess that's one of the questions we get is how do you make sure that you're achieving the PT load? Is all deflection based. Knowing, these are linear, I just lost the term, linear elastic models, right? It's easy to tell how long or how much the PT load is approximately. The other question that we get, which obviously I think for this group probably is not as applicable, but still is, well, how much can you pull it? It all depends on the length of the plate, right? If it's a short plate, you're going to pull it very little. If it's a very long plate, you're going to get more deflection out of it. And then, yes, in the end, you bolt it and you let it go, and that's it. Fire, right? Mark just did a great job talking about it. I'm pretty passionate about this topic as well. So these products have similar limitations to the externally bonded products because in the end of the day, you can apply a cover to potentially protect the rest of the structure, but in a fire event, these would still be sacrificial, unfortunately. And then I guess in building application, a lot of it has been installed for seismic retrofit, which again, kind of the chance of both the fire and seismic happening at the same time is so limited that this is, I would say, where the majority of the applications are. So in this particular structure here, you can, the FRP was installed along the height of the building, and you can protect it, again, from the outside world by putting an aluminum casing or something like that to, just so that nobody goes and touches and plays with it. Okay, how am I doing? Few case studies. Okay, good. Okay, so in buildings, again, you can utilize it for slab and beam strengthening, seismic retrofit, strengthening due to changes. I'll talk about a case like that, like if you're removing columns, for example, in an area. Anytime you have serviceability problem, PT members as well is good application, and cracked concrete that I'll talk about a case study for that water tank. So in this first example, this is a Swiss project. A lot of these are international projects, FYI. This one, there was a paper plant where they actually were going to install a new, or they're utilizing a new machinery to carry I guess the paper, really. You'll see a picture in the next slide, in and out of this section. You can see here there's a very deep beam, and the columns in between them were at a certain distance, and they needed it to be wider. So what they did, they basically installed the PT strand, or the PT system, inside the column here, and then they cut off the columns, and they rebuilt them on the side here, and now you can see how that machinery is able to move in and out of the area. Here's an example for change of use or serviceability. This was a casino in Vienna where they were making changes to the structure, and they needed to remove these two columns that were on the way here. The engineer determined that there was going to be too much deflection, and so they utilized this system specifically to address deflection, more so than ultimate state. As I mentioned before, this system is very widely used for seismic retrofit, specifically in masonry structures. We have many, many case studies of that. But just in general, I guess here's another. I'll start with this one first. This is a project in a mall where they had a new building coming in and joining an existing building. And at the join there, they determined that for seismic reasons, they had to close or stiffen that joint there. And so they utilized the PT system basically to stiffen that area for seismic purposes. This is another project in Switzerland, a very nice sized project at a hospital there. Again, it's funny because I'd never thought that Switzerland has seismic issues, but I think about 10 years or so, they came with a code changes that requires a lot of the country to upgrade their structures for seismic events. So they do a lot of seismic strengthening there. So anyway, in this one, they used about 160 systems, both for vertical reinforcement of the walls there, as well as, again, similarly, this is a Y-shaped structure. At all these joints, they installed the system to stiffen up the area for seismic retrofit. These are some pictures. You can see how, once they remove the plaster there, the FRP goes right against the wall there, and it's easy to cover it up afterwards. This was a building where they installed, again, a high-rise structure. They installed, for seismic retrofit, some of these joints were determined to not be sufficient, so they installed it along the entire height of the structure, making sure that the coupling joints, I guess, are able to take some of the seismic loads. Many of the applications for this product is also in bridge applications. A lot of it is for damage, impact, so for good emergency applications or emergency case applications. We've done some cases for, and I'll show a really good case study for higher loads. We've done a case in Mexico where they literally needed something to just have a big load that the bridge could not take for one load only, and that was it. It was a new boiler. And that's it. And then they paid for it for it to be strengthened. And this was a quick and fast way of applications for that high load demand that was required. And of course, corrosion problems. This is the particular project that I'm talking about. So they had limited. They couldn't really mobilize very well, right? It's very high. I think it's about 100 feet up in the air. So everything had to be done from drop lift, or not drop lifts, but structures built underneath here. You can see all the pre-strands were down, it was very congested in the bottom, but up here, there's not much going on. So the way we did this, we utilized 48 systems for all the beams included in here. We basically drilled a shear pin through the member up there to carry the load with four systems per beam member post-tension. Oh, yeah, here's some dimensions. Yeah, okay, 65 feet up in the air. This was the other project in Slovakia, sorry, where a very thin slab here. It's a precast box girder. And I mentioned before there's very limited flow to traffic that had to be, like you couldn't really interrupt the flow of the traffic because it was a major artery. So in this case, the background story is that the government bought heavier trains, for new rails, or for rails that were already there, but the trains were heavier, and these two of these bridges were determined to not be able to carry it. So they utilized this product for both those bridges. This is the second bridge that was done, very similar application. I mentioned before here that, how the anchors utilized. We had to do, I think, 16 Hilti anchors to distribute that load in a much larger surface area and at much lower depth of drilling that had to be installed. The other thing that's interesting is, because they couldn't drill into the slab itself, in order to make the FRP flush to the substrate, they actually had to build up, you can see in here, about 2 inches of what do they call it? Like a little bridge, so that the plate goes flush onto the structure. All right. This is an example of the water tank that I was referring to earlier, where they utilized, there was a lot of cracks on the existing structure. Obviously, after injecting and doing the proper repairs, they utilized the PT system to kind of hold it all together to make sure that those cracks don't open further. The post-tensioning was done on both sides, as shown in here, and yeah. All right, I just want to mention this because I know some of you guys will be interested. One of the things that we say, and that's interesting about these products, is that it has very little to no relaxation. They've done testing, lots of fatigue testing, as well as they've done testing for the past 10 years where they post-tension it actually to higher loads than what we designed for. And again, there's barely any losses overall on the tendon itself. So, that's one of the advantages we highlight compared to your steel application. So we do have documentation as well if anybody's interested that we can share with regards to the design. But I hope, what my goal is today is the main takeaways for this is that these products are very lightweight and they're fast to install. Obviously, one of their big advantages is they're not corrosive. And hence can be a very good application for cases where you have a lot of corrosion. We have a lot of experience with designing with some of these systems, and even though the anchored side can be complex sometimes, there's many examples that can be provided to kind of assist determine what would be the best way to introduce these loads. So with that, I feel uncomfortable because nobody else had but here's my contact information if anybody wants to reach out. Thank you all, appreciate it.
Thank you very much. I'm sure you'll have questions.
Oh, yes, I always get excited. All right, please. Yes, please.
In 2000, after 10 years of research work, we designed and constructed 3-span bridge with external post-tensioning draped cables.
Okay.
And the cable is about 14 millimeter in diameter, and each cable is stressed 150,000 pound force, 600,000 pound force per beam. Externally draped.
That's high. Uh-huh.
It's a large amount of force. The challenge, and still a challenge, is the anchoring system, the creep. So we have been monitoring this under a contract with FHWA since 2000 until 2025. So my question to you did a great job. I have to tell you that based on all the work that we have done. So how would you monitor a bridge anchoring system? That's what concerned me, the anchoring system.
Thank you. So, it's funny, like, in Europe, they can be black and white, which is great, right? Sometimes, for purpose of being straightforward is great. But then some cases like this one, every time I would hear my counterparts in Europe say, there is no creep, there is zero creep. I'm like, oh, I don't know, it makes me very uncomfortable for that same particular reason. To be honest, I don't know if we have any monitoring on the anchor side itself, and I appreciate you bringing that up, and I will make sure that, the good news is these loads are much lower, but I don't think, it should change the fact that it should be monitored and looked at.
If you would like to look at some of the results published in BCI and the years of monitoring, and we're going to continue this until 2025.
Yeah, I'll get with you because I'm definitely interested. Awesome, great. Okay. Yeah,
The
please.
blue jacket.
Thank you for your presentation. I do have two questions
Sure.
pertaining to the anchor. The first question is, any concerns with, I believe you said it was a steel anchor, so
Yes.
any concerns with galvanic corrosion with the pinching of the steel anchor, the galvanic corrosion between the steel and the CFRP plate at all?
Oh, that's a good question. I mean, I believe everything that's used, well, I know for the anchor itself is hot dip galvanized, but I think for the plates itself, I'm assuming somebody thought of, I'm not sure what the material is.
Okay.
Maybe I'll
Okay.
follow up with that, to be
I think
honest.
the epoxy.
Because that's a good question.
Or the sheet will.
Yeah,
I think
normally
the
it's what we-
system has that looked after.
Yeah.
Okay. The second question pertains to, like, were there any acceptance criteria for the development of this anchor? Was it inspired by, because I'm pretty sure there's like, those are pretty silent, your guidelines are pretty silent in terms of acceptance criteria for the development of mechanical anchors for CFRP. So how did you guys create your own acceptance criteria to say like 50 kips is suffice, given that the maximum is I think it's 120 kips?
Yeah, that's a good question. Again, because this was developed in Switzerland, I know that some of the testing that was done was definitely per the criteria in the Swiss codes that they have, or European codes, I should say. I don't know where that 50 kips come from, but I do know that, I think, and probably I'm sure others will know more than me, that the stress limit when you start seeing issues with creep, with carbon fiber, I think it's like a 45, a little bit above 50%. So I think, I'm assuming based on that research data, maybe that's where they limit it.
Okay.
Yeah,
Thank you very much.
you're welcome, thank you.
Well, along with that,
Sure.
acceptance criteria, you got different anchoring systems, so.
Yeah.
I mean, to me, that goes in with the acceptance criteria to be able to bring it and use it in American.
Yes,
North
yes,
American.
thank you.
Rafa?
Just want to comment on that question about the galvanic corrosion. There is no contact between the carbon plate and the steel. All those pieces that you have seen are the wood, but I guess if there was a barrel where you have the plate and inside this barrel and there's an epoxy. So there is no contact at all between the carbon and the steel in the system.
Okay,
So
good.
do you have any limitation about the temperature? I mean, high temperature, is it going to affect relaxation, or low temperature, brittleness? I mean, what is the limitation?
For the high, I mean, the temperatures for the, I guess on the high temperature is similar as your externally bonded FRP, which is I think 140 F. The TG of these epoxies is a little bit closer to the 200 range, so I think we keep it 140 F or so. The lower end, that's a good question. I don't know. I don't think, but I think from my basic understanding again on FRP, generally, because the carbon has a negative coefficient of thermal expansion, I don't know if it's as much of an issue.
Did you want to comment on that one too, Rafa?
Yeah, maybe, please.
When EV mission has a zero relaxation, we have done tests long time ago with one, about 20 some years ago, and it was very, it was not, didn't show that this is a documented effect.
Thank you.
You lose a little bit of pre-stress, I think,
A
but you
little
just,
bit, and then most of the loss we've had is that the anchor seating, as Professor mentioned, but from the relaxation it's almost zero.
There you go.
Yeah.
but yeah, you will get depending on your temperature range, you'll get fluctuation in the pre-stress level as
Yes.
temperature changes, yeah.
So,
Kent,
for one, we need to find a publication.
Then Mike, and then I think
Yes.
Okay.
we'll get you off the hop. Sorry.
No, it's okay, I love
Nice
it.
presentation, Eric.
Thank you.
Especially in the rapidly deployable applications.
Yes.
The emergency applications are the ones with a 100-foot tall bridge. How much curvature can you get out of this thing? And I'm thinking about the use of king and queen posts, which are obviously making the system much more efficient if you've got the room for them and maybe an emergency environment. Can you handle the kind of, what sort of degree can
Yes.
you handle and around what radius?
I'll get with you
I
because
know
I'll
I've
see
seen
you
that.
afterwards. There is a limit that we have, absolutely, because we also sometimes, in cases where you can't go flush to the surface. They do build a, oh my gosh, I'm blanking on the term, but they basically deflect it. Yeah,
Saddle point.
right. The saddle point, they do deflect it. There is, and same as for the tanks. So there is a limit. I just don't remember on top of my head what it is. It's like every 2 feet you can have like a couple of inches or something like that.
Yeah, 'cause I'm thinking about it as a king or queen post. It's a with two straights coming
Right.
down, so you've got to have your radius.
Yes.
It might be too small.
Yeah, I'll follow up for sure.
Mike, we'll let you end the session since you started.
Thank you for the very, very good
Thank you.
presentation. So I did a similar thing in my PhD work. So when we work with DOT, one of the biggest concerns is how do you inspect the system? So with the bounded, it's hard. Like you mentioned, not unbounded. So do you have any doubt about inspection? Because like normally, like DOT, if you install the entry, they are not going to install a fancy CFRP to do that. They
Yes.
only have third-party contractors to do the very basic inspection.
Right.
So how do you have any idea of what your company is doing?
So the only one that I'm aware of that's a bit more, intricate, it was in France that they required actually optical gauges be installed both on the FRP and this one to compare it. And I think we have some research data on that. But other than that, I mean, other than visual inspection, and then I guess checking the end of the end anchoring system, that's
They
Yeah.
typically do is that they mark the position in strand and then just, with lines and then just go back
Look-
and check
look
if the
at it.
lines are moved from where their starting point. That's usually, just to make sure that they didn't have any slip.
Hopefully get the same person every time.
At the same time, with the same couple of
good one.
Well, thank you very much.
Thank you all.
Jerry.
Appreciate it.